One thing I'd asked somebody a long time ago was, how does this service Shazam works? And Shazam, for those who don't know, is a service where you can hold your smartphone up, press a button, it listens to a song, and then it tells you who the song is by and you know what the song is called. And we had a discussion, and you'd done some research into this, and you'd be able to show us how it works.
Yeah, well, I have looked into how they've done it over the years, and I'd imagine the way they're doing it now is vastly more superior than the original algorithms that people proposed they were doing. And obviously we don't 100% know how they're doing it. They've given away some of the information, and then other people have kind of speculated and written up their own papers on how things will be done. But what I've actually done is written a working model, kind of like a Shazam simulator, which when we were setting up the Zoom call for this, I put in the subject line Shazam. So we're going to call my service Shazam. It does work. I mean, I've only got a few songs that we're going to load into it and test with, but I was going to go through how I think that at least the original version of Shazam worked, even if it's not the same now.
Fantastic. And I know that you've put it on a website so people can go and have a play with it, and we'll come to that in a bit.
Yep.
I know that somebody I spoke to said, oh, they must do it with beats per minute, which is, you know, how fast the tempo of the song. Is that what it's doing?
That's kind of like an emergent property. You will get a certain amount of beat detection and other bits and pieces. But the first thing to do is to run an FFT over it. It's kind of slice the song into 100 millisecond chunks.
What's FFT?
A fast Fourier transform. That's probably one of the most important bits of the whole thing. And what I'm going to do is give you the quickest and most basic explanation on what it does. I'm going to give you a pound shop version of it now, or in America, dollar store version of it. Okay, so we got a nice little sine wave, which all computer people seem to be very bad at drawing because we spend more time typing. But let's say that this here, the period between this is 100 hertz, which means 100 times per second that it goes through its cycle, right? If you imagine that you had a clock with a single hand on it, and that clock is spinning around at a rate, so we're going to imagine we've got this clock and that hand is going around at a particular rate. So let's say that clock is totally in sync with the sine wave. So the sine wave is 100 hertz, 100 times per second, and the clock is going around at 100 times per second, which may seem fast, but for audio, that's very, very slow. What you'll end up with is you'll end up with a correlation with the wave that's coming in. Just as a quick recap, when you're sampling on a computer, when you're sampling a wave, effectively you are just taking a reading of the voltage. The middle of it is 0, and above it you consider positive, and below it you consider negative numbers. So that's all we need to know for this. So what we're going to do is imagine you've got this clock that's going around at 100 hertz, and the hand is at the top. And let's say we're right at the peak of one of the waves. So that's going to be the highest bit. So let's say that's 100 from the 0 point. That value is 100. So in this clock, let's say we're going to plot a point here at 100. So the distance there between the center of this clock and there is going to be 100. Now, as you come down the wave and you get to the trough at the bottom, halfway through the period, that hand is going to have turned round to be exactly 180 degrees round the other way. So that hand is now down in that direction. But of course, your number that you're plotting is a negative number because you've come back down the other way. So you're plotting in the opposite direction. So what you'd end up with is the point on this clock that you're going around, the point would be in exactly the same place as it was when it was at the top of the sine wave because it's in the opposite direction. Now, if you have 100 hertz sine wave coming in, the data, all the volume levels of the sine wave coming in, it's 100 hertz, the data's coming in, and your clock's going round at 100 hertz, what ends up happening is you can end up plotting the same point all the time because it's hitting all the peaks and all the troughs. And if you've got a sample rate, which you would have, which would have many, many more slices than just getting the peaks and the troughs, what you end up with is a load of other scattered out noise. And if you take all of those points, so let's say we had a point there and a point there and a point there and a point there, well, all of those points that are surrounding it, if you use complex maths, basically you average it and reduce it down, and the noise will cancel itself out and you'll be left with a prominent point on your 2D graph, and that prominent point will be how loud that particular frequency you were feeding in is within that particular signal. So if you were then to, say, put in 101 hertz, but you've got the clock going at 100 hertz, although you will get some correlation, it's not going to be as much. And then 102 hertz is going to be less correlation. It's going to keep going down until effectively it will just turn into noise and all of those points will cancel each other out. So if you want to find out how much 100 hertz, 200 hertz, 300 hertz, 400 hertz, and you want to keep going, you have to effectively run a sine wave through and do a comparison to the original signal, plotting these points, average them down and see what's left at the end of it. So if you wanted to do it for 100 different frequencies, you'd have to do that 100 times. There are libraries out there that do this stuff super fast, super reliably, and much better than I'm ever going to do it. But the whole point of FFT is you put in an audio signal and you get out the component frequencies. So, for example, if you had a sound which was like a piano, so you're playing an A on a piano, it'll be 440 hertz will be the main fundamental frequency, but then there'll be harmonics within that, and then you'll get the octave up at 880 and so on, keep doubling the frequencies, and they'll fall off. And it's the mixture of all of those frequencies together that give you the sound, and it just doesn't sound like a pure sine wave.
So when you combine all of those different elements that make up that note, those different elements make the note sound like it's a specific instrument or
Absolutely.
A specific source.
Yeah, guitar will have different harmonics to a piano. They'll also have a different, some instruments will slowly rise to a peak of a sound. Some will come in and be very percussive and have what's called a transient at the beginning of it. So when you have all of these different sounds, they're a combination of lots and lots of different sine waves at different frequencies. And when you put them all together, they produce one waveform, which is a lot more complicated, which is the music you listen to or the speech you listen to or whatever. And FFT and Fourier transforming basically is a way to get those fundamental frequencies back out of the song. So if you've got a song and you've got loads and loads of different frequencies and you want to say, do I have 50 hertz playing at this point? Do I have 250 hertz playing at this point? You're effectively running it through and doing a comparison to a raw 250 hertz signal. Do this clock thing, plot your points, and do an averaging to find out. And basically, however far away the point you're left with is from the center of the clock is how loud that signal is within that particular bit of data that you've given it. And although it doesn't matter in this particular case, sort of where it's offset, as in like 12 o'clock, 1 o'clock, 2 o'clock, whatever, is actually also the phase, is how the wave is shifted. But we really don't need to get into that. For the purposes of this, we're just basically getting out what frequencies are being used. And obviously, the more frequencies you want to test, the longer it's going to take to do.
So we've got a very complicated waveform, which is maybe a musical song with a bass and a drums and guitar and piano and all these different things, which has become one waveform, but it's an extremely complicated waveform because it's made up of all of these different instruments, which in turn are made up of all these different harmonics and different elements. We're using FFT to look at a musical track and to pull out some information about what frequencies are recurring. Yeah.
When we get our song, let me change sheet of paper here. If we have a song coming in that's like a complex waveform, what's going to happen with that is that will be made of a set of frequencies, and we want to get those out. And really, all we're interested in is between maybe 100 hertz, which is quite low. It's not super sub bass, but it's low enough that a phone would be able to pick it up accurately. And then say about 5,000 hertz or 5 kilohertz, which is quite a cutting sort of frequency that hurts your ears. Obviously, the higher the frequency of the data, the more intricate data there is in there, but the more noise you're going to have when you're trying to use a phone to record something in a loud environment or with some background noise. So what we're trying to do is pass through this complicated waveform, and we're really interested in looking at frequencies between 100 hertz and 5,000 hertz, 5K. Now, the songs that I'm dealing with here are sampled at 48K, which means you can accurately represent a 24K signal In reality, the way Shazam would do it is they downsample that. They don't need huge files with all of that top end on it. I just had them at that. So if you had 24,000 different frequencies you were looking at with that you got back, you would end up with 24,000 different numbers and one for each individual frequency. Obviously, that would take way too long. So the one that I actually used, if I look at my code here, I've got an FFT size in my JavaScript at the top here. The FFT size is 2048, which I believe will return 1024 individual frequencies. So if you were to split up 0 to 24,000, divide that by 1024, then you work out each frequency chunk that it's looking at. So basically we're looking at about 23 hertz, 23.4 hertz per slice that we're looking at. So this waveform, this complicated song waveform, is going to have a reading. It's going to have let's say a figure between 0 and 1 of how loud that is. So 1 is the loudest possible, 0 being the quietest possible, and we're going to have that for 23 hertz chunks all the way up from 0 to 24,000 hertz, and we get that data back as an array.
You'd feed a song through this system that you just talked about and effectively pull out that information, pull out that data.
Yes, effectively pull out the data on each frequency. So if there's a lot of low frequencies, if there's a load of going on, you're going to get more stuff happening in the lower parts of the array. And if you've got a load of top end stuff happening, you're going to get it in the higher elements of the array.
This is what they would do to all the source music, all the originals. Is that right?
Yeah, so they go through and get this information out. So then there's another stage beyond that. So once you've got out all this information, so let's say we've got all of these different frequency ranges, and at each frequency range, we've got effectively a volume level. How loud is it? And we'll say, for the sake of this, between 0 and 1. Okay? So we get out how loud that is, and we then want to effectively group some of those together. So we want to say, well, anything that's within this range, we'll kind of say this is all one bucket. We'll call it a bucket of frequencies, right? And all I'm interested in is in this bucket of frequencies is which one of those is the loudest one. And then I'm just going to get rid of everything else. I don't care beyond that. So if I've got, say, 100 hertz all the way up to 5K, 5,000 hertz, okay, so we've got these 6 frequency buckets going up. And all I'm interested in is I want one frequency in the bottom bucket. I want one frequency in the second bucket. I want one frequency in the third bucket, and so on, so that I get the most prominent frequencies. And then effectively with that, I'm going to draw a dot. I'm just going to call that a point on my graph in each one. So we should get 6 dots out, maximum of 6 dots per slice. And if you have each column as 100 milliseconds, so every second you're getting 10 columns of this audio, suddenly you've got a nice little graph with lots of different data points in slightly different places. And I think the best thing is we just show it on the screen.
Just to make it real for people, is 100 hertz something like a bass guitar or something like that? Can you give us a couple of examples of those?
Different instruments, they don't just have one frequency spectrum, they'll have a whole vast range of frequency spectrums. And part of mixing and being an audio engineer is finding ways of putting all those together so that they sound nice, and kind of thinking, well, if I lose that bit of frequency spectrum off the guitar, then the bass can go in and take the same space and it's not going to interfere and sound horrible.
So it doesn't get too muddy, okay.
But different instruments will have different areas of the frequency spectrum that they take up. So bass drum will be right at the bottom, and then I'd say bass guitar just above it, and then you'd have sort of snare drum around 200 hertz. You'd have guitars produce a lot of sort of 400-500 hertz, and then vocals can really kick through at about, the prominent frequencies, sort of 800 to 1,000. So then it starts getting cutting around that area, and then all your is happening, and sort of at the 4,000 to 10,000 hertz range. And that's where the prominent frequencies are. Obviously, a guitar will produce 50 hertz, and it will also be producing, 12,000 hertz. But it's where the most prominent frequencies are for that instrument, and that's the important thing. And generally, when you play a note, you will have a thing called a fundamental. So if I was to play that A at 440 hertz on my guitar, it's going to produce loads of other lower and upper harmonics, but the most prominent frequency will be that 440 hertz, and that will be the fundamental. And what we're really looking for is fundamentals within our frequency buckets.
How do we look at those on a screen?
Well, effectively, it's a two-dimensional graph. You have time along the bottom, and you have frequency up, and actually, I say two-dimensional, three-dimensional way, because the colour that's actually plotted in those, instead of it being a number, you display it as a colour. And traditionally, you know, blue will be quiet and red would be loud, or going into the oranges would start to get loud. I think the best thing is if I play in a song, you'll hear the song, it will go through in real time, it will scroll across, so you'll see the x-axis kind of populating, you know, as time goes across, and then you'll see all the y-axis filling up with all the different colours and the data points that it's picking out. And effectively, under the hood, it's testing each 100 millisecond slice with a load of different frequencies using that clock method or something similar, however the FFT algorithm they've implemented is doing it. And it's just letting me know how loud it is. And actually the numbers I get back are between 0 and 255.
Okay, before you do, I want to avoid any imperial entanglements. Tell me the music that you're going to use. It's not commercial?
No, it's not commercial. This is all music that is stuff that I own, that I've either written or been part of with.
Okay, cool. That's all right. I just
had, you know,
I'm looking up at YouTube here.
So what I've got here, if you look at the screen, we're going to ignore all this stuff at the bottom at the moment. And what I've got these 5 light blue songs, which are actually full tracks. I'm not going to play them all in because for the purposes of the demo, we can use the intros of the songs. So I'm just going to play a little bit of each of them. And then here I've got 10 clips. I've got a clip of the music recorded through my phone.
So these are to emulate somebody sampling the sound.
And the 0.1 clip is actually pretty much the same thing where I've recorded it through my phone, but I'm also talking over it. So try and emulate some background noise. So we've got 2 different tests there. But the first thing I have to do is play in the raw audio to the system. The whole of this, following on from our last video, the whole of this demo I've done with JavaScript, CSS and HTML5 as well. And I've been using the web audio API, the audio context stuff, which has a lovely analyzer that does all the FFT for you, all built in under the hood in the browser, which is wonderful. Let's click on the first song and we'll see it populate. That's enough of that one. Now I've clicked on this song, because I put this together as a demo and it's not something where I've labelled it all up as an actual piece of work that's being published. When you've analysed the song, it then appears in the list underneath as a green button that you can click on, which we'll get to later. So effectively, once I've played them all in, we're going to end up with this blue row here being duplicated underneath in green, and it should look pretty much exactly the same, apart from the fact that the buttons will be green. But that means that they've all been played in and we've got a noise fingerprint for each one. Let me play in the other ones. It's quite nice to see the bass being drawn on this one. The most interesting thing is obviously that song there, 2020 Rendezvous. There's actually a remix of that, which chord-wise sounds similar tempo. It's about 2 BPM difference. It's got different drum sounds and stuff, but it'll be interesting to see how it can differentiate between effectively the same song but in a remix fashion. But let's do the others. Right, that would do for that one. Next one. Mm-hmm. 2020 Rendezvous remix. Last one. Okay, so that will do for that one there. So what I've done is I've got all the songs in here now, and before I do the clips, because we've got a song up, and this one's particularly good on the screen at the moment, what we're seeing here is you can probably see in the pixelated chunks, particularly if I zoom in on it a bit, you can see these tiny little sort of 100 millisecond slices. So as you can see, we've got these 100 millisecond slices, and then the yellow marks are where the most prominent frequencies are. And I've effectively split this up into 6 different chunks. That can actually be changed down here. If you wanted to change it, you can say maximum points per slice, and you can actually change that as one of the variables. But you can see clearly where like a cymbal or something has been hit, where you're getting a lot of data on each beat. So you can kind of see the tempo of the song. As it's playing through the music, you can see the bass line moving. I think that's kind of cool. But if I now play in these clips, and these are tiny clips, these are sort of like 5-6 seconds, what you get if you were listening off your phone. So we'll just go through and play all the clips in. This is called 1,000 Things. This has got no name, we simply call him Cat. Blah, 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 blah. Just chatting over it like you're having a conversation in the background. So there we go. So now what we've got is we've got all our 5 songs in, and then we've got 5 clips of just the song recorded through my phone, and then you've got another 5 clips where I'm clearly chatting over them, whatever came into my mind at that particular time, which was just nonsense, but I was just emulating background noise. Now the idea is if I click on any of these green ones here, it will then compare it to the songs, the first 5 songs, and we should tell how well it's correlated, and this will be the big reveal. Does it work? So I'm going to click on one and let's see. And there you go. You can see at the bottom there, it's correlated the first clip to 1,000 Things really well. Go clip 2, and it's correlated to the second song. Clip 3 to the third song. Clip 4 to the fourth song, and clip 5. Oh, I didn't actually.
I think you missed 5.
Missed 5. Oh, let's analyse that one. So if I do clip 5, which has now ended up at the end there, that's actually correlating there. You can see it's correlating a bit with 2020 Rendezvous that's not a remix.
So that's the same song, but just different kind of versions of it, right?
Different version of the same song. It's got the same melody, slightly different words. It's about 2 BPM faster. So I'll explain on the paper in a minute how this matching happens. If we go to the other clips here, so clip 1.1 should be 1,000 Things, even though I'm talking over it. And then it goes down to there, to the second song, third song, fourth song, and then the 5th one with me talking over it selects the last one. So it is correctly identifying all of them. And the way we do that, turn over the bit of paper, is when we have this set of slices. So we've got these 100 millisecond slices. So we've got 6 points on there, and then we've got in the next column over, we'll have a slightly different set of points in slightly different places. I was effectively going through and numbering all of the points. So the first bottom-most point we'll call 1, and then we'll work our way up the column. So we'll call that one 2, 3, 4, 5, 6. And then when you get to the top and there's no more points to go, you go to the next column, and then 7, 8, 9. And effectively, you're creating an array of these points, but with the frequency of that. It won't exactly be the frequency, it will be the position within the array which will be set, but it doesn't really matter. The position within the array represents the frequency. So what we're going to do is we're going to take, say, the first 5 frequencies. So all we're doing is matching the first point. So let's say I've got this graph here, these X's on a graph for my original song that I'm trying to match against. And then I've got the clip that I've recorded from my phone, and that's also got these points. All I'm trying to do is just match the first point. If I've got a point at 100 hertz in my sample from my phone, and there's a point at 100 hertz in the original song, we can then work from there. If there's not a match on that first point, we can move on. You know, we don't care about that. We can move on to the next thing. So from there, we've got the noise print that comes in. Now, the noise print that comes in your phone may not have all of the same frequencies exactly the same, and you might have less top-end frequency or less bottom-end frequencies. So we're not trying to match an exact pattern to the original one. What we're trying to do is pick one anchor point and then say we want X number of other points that were within what I've recorded off my phone to match within a song. And it doesn't matter if they match in the right order, as long as the frequencies are there. So in a way... you could sample have more maximum points per slice for the original song than you would off the phone if you wanted to. You could have less data points for the information you're getting off your phone.
For the quality of the microphone on, say, the phone in this instance doesn't affect the frequencies, does it?
It will for the absolute bottom and absolute top end. If I play an A chord on the guitar and I recorded it into a really bad sort of old school dictaphone or a really awful like iPhone 1 or something that doesn't sound good I don't even know whether they had a voice notes app, but let's say I did that. You're still going to be able to get out usable information and hear that I'm playing an A chord on a guitar. Okay, it's not going to sound beautiful, but I mean, it rarely does when I play. But it's still going to be a representation of an A chord. So as long as the prominent frequencies are there, and you've got some kind of system to kind of match them up with the original song, it will work. So what you end up with is these groupings. So these groupings will be, if I've numbered all my points in my sample and I've numbered all the points within the original song. I mean, actually, forget the original song. That doesn't really matter. We'll number the points within the sample I've got from the phone. We're going to test. We're going to look for point 1 anywhere in any of the songs. And then if we find point 1, we're then going to try and match points 2, 3, 4, and 5. And if we look within that 100 millisecond slice or the next 100 millisecond slice, because particularly with lower end frequencies, they resonate in the room, so they could last a bit longer if you were recording in a room compared to having the original recording. So you might look over into the next slice and see whether the frequencies are there. And obviously, if your first anchor point is actually at the top and there are no more frequencies in your column, you've got to go to the next column. So effectively, you're looking for 1, and then if you find it, you test 2, 3, 4, and 5 against the original source. And if you get a match, you just add 1 to the match score, and then you move on. You set point 2 as your anchor point, and you try and match 3, 4, 5, and 6, and then you set point 3 as your anchor point. So what you'd end up with is drawing a line around that lot there, and then I'll get a red pen to do it in a different colour, and then the next one we're going to be testing are that lot there. And then if I go to a green pen, the next lot I'm going to be testing is this lot here plus this one at the bottom of the next column. What I'm interested in is the distance from the anchor point to the next point, and then from the distance from there to there, and the distance from there to there, and then across to there, and then across to there. And I'm happy to find, say, this third point. I'm happy to find that in the next column. That would also be a match in the next column across, because you don't know at what point you're taking these 100 millisecond slices. You could be slightly out of phase with the original. So something that appeared in the same column on one would appear across 2 columns because of the timing. So these are all the tolerances that I'd imagine Shazam have been through and tweaked and gone crazy on to the nth degree. All I'm really doing is just looking for these maximum frequencies and then using an algorithm to match them up. And it works really well, and it's really fast as well. The naive approach would be to try and match up the whole array of all the noise print in a 5-second chunk to all the other array, and effectively you get this huge convolution going across the whole thing. It'd be like this huge convolution filter going across the whole thing, which, you know, computationally would just, I mean, I did that initially. That was just to check that things were working. I knew it wasn't going to be how I ended up doing it, but to do something with 5 songs that took me no time at all, I clicked and it had matched it even in JavaScript and HTML5 as my UI. It was taking maybe 10, 15 seconds to search one clip against 5 songs with it, doing it as an array match. Whereas doing it where you have the points and you just anchor off the first one and you look, just seemed really instantaneous. And then of course, if you put those little 5-point groupings or 6-point groupings and you somehow represent them in a hash table, they'd be very, very quick to look up in a database, and you could use all sorts of clever computer sciencey stuff to make the algorithm work even faster. So you're holding it and it just tells you the song straight away.
If you're playing on, say, an old-fashioned turntable, my memory of these things is that they can play at slightly different rates, and then presumably that would affect frequencies, would it? Well,
it would. So technically it would, but it all depends on how big your FFT bin is and how many...